F is equal to C minus P plus 2.
F is equal to C minus P plus 2. What is reduced phase rule? What do you mean by reduced phase rule? Hmm? F is equal to C minus P plus
1.
Plus.
1. Yes. So it is generally applied to which system? The reduced phase rule. Generally applied to two component system.
Temperature, pressure.
Yes. So keeping one variable as constant, so we can have reduced phase rule, which is F is equal to C minus P plus 1. So this can be applied to generally two component systems. So in two component system with phase is equal to 1, then so what is the degrees of freedom? In with the phase is 1, what are the degrees of freedom as per phase rule? It's 3. F is equal to C minus P plus 2. That is the phase rule. So P is 1 and so C is 2. Then the F is equal to 2 minus 1 plus 2. So it's 3. So degrees of freedom is the highest order is 3. So in two component phase diagram, so maybe represented by 3-dimensional diagram of pressure, composition, and temperature. So in this diagram, two axes represent two variables. So while third variable is constant. So phase diagram may be constructed as pressure, temperature by keeping composition as a constant. Composition or concentration is a constant, or you can plot a phase diagram between pressure and composition by keeping temperature as a constant, or temperature and composition diagram by keeping pressure as constant. So generally when you keep constant of pressure, then you can neglect vapor phase, because there is always if there is more pressure, there will be higher vapor pressure, vapor phase. So since you keep pressure as constant, so we can ignore vapor phase. So in that case, so you can reduce the phase rule to F is equal to C minus P plus 1. So this is called a reduced phase rule or condensed phase rule. So that means you can have a and look for condensed phase rule. So here in phase diagrams, so what we take the variables, the temperature and the composition. So to represent the solid and liquid equilibria. So this two component system is generally classified. Generally, depends upon the miscibility of two components in molten state, and also on the basis of solid phases that separates out on cooling. So generally, when you mix two metals, or when you mix any of two things, generally you always find some miscibility or immiscibility, or compatibility or incompatible, right? So it is here in two component system. So you can classify classification depends upon the mix in molten state. So that means the temperature, and also on the basis of solid phases that separates out on cooling. Okay, so when you heat up to till the melting point of the two metals or two components, so it may be miscible. But again, when you cool it down, again it may you find phase separation. So when two components, that are completely miscible in liquid state, so that means the molten state, they are allowed to cool at lower temperatures, and components begin to separate out as solid in three forms. So when you heat two components and you allow them to cool down, so there will be phase separation. So the phase separation could be in three different forms. For example, the two components are not miscible in solid state and form eutectic mixture. So if the two components are not miscible in solid state, so after cooling down, it's called eutectic mixture. For example, lead and silver alloy and cadmium and bismuth alloy. These two examples are called eutectic mixture. And the components form a stable solid which melts at constant temperature to give a liquid with same composition. So such compounds are said to have congruent melting. For example, zinc and magnesium. So the second one is called congruent mixtures. So that means they form a solid compound, so which melts at constant temperature to give a liquid with the same composition. So whatever the composition of the solid, the composition will be the same even after melting. Okay, the composition in the solid form is equal to the composition in the melt form. So it is called congruent melting points or congruent mixtures. For example, zinc and magnesium. So third one, the components form a solid compound which is unstable and decomposes below its melting point to give a new solid phase and liquid. So that is different in composition from its original compound. So these are called incongruent mixtures. So that means the composition in solid form is not equal to the composition in the liquid form. I mean molten in the molten state. That is called incongruent mixtures. For example, sodium and calcium system. So sodium and potassium. So eutectic systems, the first one. So it's a two component system. So both the components are completely miscible in liquid phase, but they do not react chemically. Okay, so two component system. So they are completely miscible in liquid phase. I mean, when you heat them up, so they are completely miscible, but they don't react chemically. It's called eutectic system. For example, silver and lead. And here there are in eutectic system. So there are two important parts: eutectic temperature and eutectic composition, and eutectic point. So what do you mean by eutectic temperature and eutectic composition? So for example, when you take silver and lead, start from 0 to 100% silver and lead 100 to 0%. So you can vary the composition of silver and lead. So at one particular composition or at a particular temperature, the silver and lead system. So there will be equilibrium between solid and liquid. So that is called eutectic composition or eutectic temperature. So for example, a pure substance, for example, the freezing point is higher and upon increasing decreases to lowest value. So for example, take substance A and substance B. So the freezing and while increasing the concentration of substance B, the B freezing point decreases to the lowest value. So this is called eutectic temperature and eutectic combustion at this state. Okay. So the eutectic point, so it's defined as the lowest can be obtained by the mixture of the two substances. So at a particular composition of the both substances, for example A and B, but you can obtain the lowest melting point. So that is called the eutectic point. Let's take silver and lead system as the example. So because it is very simple eutectic system. In this system, the silver and lead are completely soluble in molten state, and they do not react to form any compound. But when you cool them down, so they form as easy melting mixture. So it's a eutectic system. So there is possibility for 4 phases in equilibrium. So one is solid silver, solid lead, and the melt of lead and silver, and the vapors. The boiling point of silver and lead is high, so gas phase is substance. So pressure has a negative, so it's the reduced phase rule. So the solid and liquid equilibrium, so without gas phase, is known as a condensed system. This is the typical phase diagram for silver and lead system. So x-axis is the composition of silver and lead. Y-axis is the temperature. So starting from the left hand side and B right hand side on the O. So O is called the eutectic point. So this is the eutectic point. This is the lowest melting point, the eutectic mixture, which is obtained through varying different compositions of silver and lead. So from this diagram, so 961 degrees centigrade is the melting point of silver, and 327 right hand side, which is B, point B. So 327 so is the melting point of lead. Okay, so A to O, the curve A and O. So AO or OA, so it says about the freezing curve of silver. And curve OB, it is a freezing curve of lead. Okay, so here at zero level on X and Y axis, so we start from 100% silver and 0% lead, and we try to increase the lead composition and reduce the silver composition. But the sum of the composition, I mean sum of the both components should be 100%. So initially we take 100% silver, 0% of lead. So then you take 98% silver, 2% lead, and 90% silver and 10% lead, 80% silver, and 20% lead, like that. So we vary the composition. Okay, so this at the point what is called the eutectic point, where we can obtain the lowest melting point of the mixture. At this point, the eutectic temperature is 303 degrees centigrade. So 303 degrees centigrade is the eutectic temperature, and 97.4% lead, 2.6% silver is called eutectic composition. Okay, and above this curve AOB, so there is only one phase, which is molten silver and lead exist. Okay, so below this OA curve, below AO, OA, and 303 point, you can name it as E, and here near OB, so you can name as a EF, for example. So below solid lead plus liquid, so you can it is the terms are missing, so you can name it as F. So AOE, AOE, this area, so there will be more solid silver plus some molten lead and silver exist. And here, so BOF, so there is solid lead plus the molten lead plus silver, molten silver and molten lead. There is equilibrium. Okay, so here the below O, I mean, for example, OE, there is a eutectic mixture of solid plus solid silver. So eutectic mixture of lead and silver in the solid form plus solid silver. On right hand side corner, so there is a solid eutectic mixture plus solid lead. Okay, so from this phase diagram, what is the melting point of silver? Which is 961 degrees centigrade. So what is the melting point of lead? 327 degrees centigrade. So what is the eutectic temperature? Which is 303 degrees centigrade. What is the eutectic composition? So which is 97.4% lead and 2.6% silver. That is eutectic composition. In the last class, we have discussed about the areas of the curves in the phase diagram in one component system. So the areas of the curves always bivariant system, and only the curve so is always a univariant system as per the phase rule. So let's go to the areas of the phase diagram of silver and lead. The area above AOB, so which is only melt mixture exists. Melt mixture of silver and lead. So area close to BOF. BOF. So F is missing. So here F is the dash line. Dash line in the so 303 is you can name as E, and opposite to that it's a name as F. So BOF. So only a melt mixture of silver and lead plus the solid lead exists. And area enclosed by AOE. So only molten mixture of silver and lead and uh, solid silver exist. Curve AO. So it says about the melting point of silver, which is 61 degrees centigrade. So the continuous addition of lead. So the curve shows that. So it lowers the melting point of silver along the curve of AO. So two phases exist in equilibrium along AO, the solid silver and the molten solution of silver and lead. So in case if you add more lead, so you can they can separate out as solid. So curve BO. So the melting point of lead is 327, and the continuous addition of so lowers the melting point. So along curve BO. And two phases, so solid lead plus the molten lead and silver exist also along the axis, along the curve. This system is so univariant. So the curve is a univariant. So AO and BO meets at point O. So it's commonly known as so solid lead and solid silver, and the liquid solution is coexist. So there is a equilibrium between the solid and liquid. So at this point of O, that which is called eutectic point. So the zero, it's a zero variant system. The point O is lowest temperature 303 degrees centigrade, at which the liquid exists. So in case if you cool down the liquid, so below 303, both silver and lead they separate in solid. So if you cool down below 303 degrees centigrade, so both those metals they separate out. So in case if an alloy of silver and lead and silver melts at 303 degrees centigrade, which is lower than the melting point of silver and Pb, it's called eutectic mixture. So as I have mentioned that, so you can divide the diagram with the dashed line, so which is you can name as E and F. So on the left hand side of OD, so crystalline silver and eutectic mixture are stable. On the right hand side, the lead and eutectic mixture are stable. So this is about the lead and silver two component system. So there are systems with congruent melting point as well as incongruent melting point. So what do you mean by congruent melting? So generally it occurs during melting of a compound when the composition of the liquid that forms is the same as the composition of the solid. So which I have mentioned before, the concurrent melting means the composition should be the same as in the solid in the solid phase as well as the molten state. In incongruent system, the composition in the solid form is not equal to the composition in the liquid phase. So after even melting and again you cool them down, then again there will be different composition. The composition is not equal to the solid composition is not equal to a liquid composition and is not equal to again the solidified after again than its composition in the solid form. That is called incongruent melting. Okay, so this congruent melting and incongruent melting it generally happens in binary, I mean two component systems. The zinc magnesium system. So it's a one example for congruent melting point. So this is the typical phase diagram for zinc and magnesium congruent mixture. So y-axis we take the temperature. So like before, so x-axis we take the composition of magnesium and zinc. So we start from zero value. So we start 100% zinc and 0% magnesium, and we try to increase the composition of magnesium and red zinc. So in the mix. So we start from the right hand side. So point A, which point A is says about the melting point of zinc. Any questions? Okay, so here there are two eutectic points and there are two eutectic compositions. Okay, so there are two eutectic points, which is a C. The eutectic temperature is 380 degrees centigrade, and the eutectic composition at this point is zinc 79%, and the magnesium zinc is at 21%. So here magnesium zinc is it's called the intermetallic compounds. And at point E, the eutectic point, again the composition is magnesium is 61% and intermetallic compound is 39%. So this zinc and magnesium system has a congruent melting point. So zinc and magnesium, so melts at zinc melting point is 419 degrees centigrade, and magnesium is 650 degrees centigrade. And in the both metals enter into chemical combination and form an intermetallic compound, so which is and they melts at 590 degrees centigrade. So this is the point D. So the intermetallic compound magnesium and zinc, so the melts at 590 degrees centigrade. So to give a liquid of the same composition. So that's why the 590 degrees centigrade is called the congruent melting point of the system. So in the reduced form, the system has the following 4 phases. For example, solid magnesium, solid zinc, and solid intermetallic compound of magnesium and zinc, and the last one, the liquid, the molten zinc and magnesium. So when you apply a reduced phase rule, so C minus P plus 1, so the degrees of freedom is 0. Therefore, at point D is a 0 variant system. And eutectic point, also point E, which is 345, which is the least melting point of magnesium and intermetallic compound of magnesium. So here also there are 3 phases existing together in equilibrium at point E. So then the degrees of freedom is equal to 0. So this is also a 0 variant system. Point C, so which is another eutectic point. This point says about 380 degrees centigrade, so which is the least melting point of zinc and intermetallic zinc and magnesium. So at this point also there are 3 phases coexist, and the degrees of freedom is equal to 0. So this point also a 0 variant system. The area above BCE, BCE it consists of a single phase system. So only the liquid metal. So liquid metal of zinc and the magnesium. The degrees of freedom is equal to 2 since it is a single phase on 2 components. So it's a bivariant system. And other areas are univariant system. So since there are only 2 phases. This 2 component system is called the congruent melt mixture. The curve BC is called the freezing curve of zinc. And there are the zinc and the melt of zinc and intermetallic compound. It's they are in equilibrium phases. It's a univariant system. And curve AE on the right hand side, so it's also called the freezing point of magnesium. So curve BC is the freezing point of zinc. Curve AE is the freezing point of magnesium. So it's also a univariant system. And curve CD, so it's a equilibrium of intermetallic compound magnesium and zinc and melt, which contains magnesium plus intermetallic compound. So there are again 2 phases. It's a univariant system. Okay, so this is all the list of the curve and the areas at this curve. So the phases, the one number of phases in equilibrium and the degrees of freedom. So mostly all the curves are univariant system, except the eutectic points with the eutectic point C and point E. So they both are zero variant or invariant. Say degrees of freedom. Degrees of freedom is equal to 0. Yeah. So this is all about the two component system of zinc and magnesium. So what are the applications of phase rule? Because you can apply phase rule in order to produce safely plug pins and soldering. For example, if you want to use two metals together for soldering, so you can determine the exact composition and the temperature at which you can use soldering of the particular mixture of metals. And you can also use the phase rule for freeze drying technique. So this technique of dehydration of food in pharmaceutical industry. What do you mean by freeze drying? Freeze drying. So generally there are three phases: solid, liquid, and vapor. Right? So in freeze drying technique, so you can, for example, so if you want to get rid of some liquids easily. So, okay, so take the liquid, you can freeze it down till maybe minus 50 or liquid nitrogen. So take the liquid nitrogen, we can freeze the solvent. Okay, so when and you apply vacuum, so then the whatever you have frozen, the frozen means is a solid form. When you freeze it, it becomes a solid. You solidify the liquid. So when you after freezing, when you apply some pressure, I mean under some vacuum, so this solidified liquid the straight away vaporizes slowly. This is called freeze drying technique. So the solid becomes vapor without going into liquid state. Without going into liquid state. So it's straight away solid to vapor. So this technique is called freeze drying technique. It's mostly used in pharmaceutical industries, food industry and pharmaceutical industries. So this phase rule you can also apply in thermal analysis of material science. So thermal analysis generally you widely use thermal analysis uh, to study the material's behavior with the temperature, the change in the temperature. For example, there are different thermal analytical techniques. They are called thermal gravimetric analysis. This is also called TG. So thermal gravimetric analysis. Gravimetry means it's a weight loss. So weight loss due to decomposition with the temperature. So when you increase temperature, so what happens with the materials? So some materials start to decompose with the temperature, and there is a weight loss of the materials. So from this technique, so you can determine the decomposition temperature of the materials. So that, so for example, so material A, so it decomposes if you determine that using TGA technique. So if you determine the decomposition temperature of material A as it is 200 degrees centigrade, so you can use the material below 200 degrees centigrade. for stable performance. DTA, differential thermal analysis. So here also you can study the behavior of the materials against temperature change. So you can study the materials behavior as a function of temperature. And DSC, differential scanning calorimetry. So here, so enthalpy is required to record zero temperature difference between the substance and the reference material. Because in DSC technique, you always need a reference material, and you can keep your own material, so you can always compare with your reference material, and you can study the temperature behavior with respect to the heating rate of the material. So by this technique, you can study. You can mostly use in pharmaceutical. For example, drugs. So when you can study the drugs behavior with the temperature here with the DSC, so you can find out what you call naturalized temperature, something like that. Even for polymers, you can determine the melting points. Even for polymers, there is particular temperature is called TG, the glass transition temperature. So it is applicable only to polymers, not to other materials. So only to polymers is a TG. So you can determine the TG and crystalline temperature and glass transition temperature and melting temperature for different materials, for polymers or even for drugs, using differential scanning calorimeter. And dilatometry. So changes in size or dimension of substance are measured using dilatometry. Also evolved gas analysis. So volatile product evolved, so are analyzed using this evolved gas analysis. So from the product, so how much volatile compounds are present with the compound, so you can analyze that. So this is all about phase rule and single component systems and congruent melt mixtures and incongruent melt